So the law that describes how the light will bend in terms of the angle of incidence and angle of refraction is called Snell's Law. And it basically says that N of the first substance times sine of the angle in the first substance is equal to N of the second substance times sine of the angle that it bends at in the second substance. Now, remember that we're always going to measure, we're going to think about that interface between the two mediums, and we're going to draw an imaginary line called the normal perpendicular to it. And the ray is going to hit at the interface, and the angle that it hits at is called the angle of incidence, and the angle that it refracts at is called the angle of refraction. So sometimes you'll see this Ni sine I equals Nr sine of R. So let's look at an example. Light is incident at 30 degrees on the surface of a lake. So if we're thinking about a lake is water, which is the N of 1.33 that you would look up, or it would be given to you. And you're going from air into that, so that has the N of 1.00. So if we draw the ray diagram, so that's a ray of light hits this at 30 degrees. Because it's going into a higher index, it's going to slow down and bend towards normal. So we're looking for R, and you notice that I draw this purposely to show that R is smaller than 30 degrees. And then I'm just going to say 1.00 times sine of 30 equals 1.33 times sine of R. So sine of R is going to be equal to 1 times sine of 30 divided by 1.33. And I'm going to take the inverse sine of those to get my angle. So let's do that. So that's going to be 1 times sine of 30. So let me get my trig on here. So 30 sine of 30 equals times 1 equals divided by 1.33 equals. So it's a number there. And now I'm going to take the inverse sine of that. Okay, let me try that one more time. Sine, I see what I'm doing. I have my calculators backwards. 30 sine times 1 divided by 1.33 equals, okay, there we go, it's a decimal. And now we're going to take the second sine of that, which is 22.08 degrees. So angle of refraction is going to be 22.1 degrees. So this number right here is 22.1 degrees. That easy. So if we wanted to do other examples, we could do these, and let's do the first example. What is the angle of refraction in a medium if the angle of incidence is 48 degrees and the index of refraction is 1.58? So we're just going to assume that we're going from air into this 1.58 substance. So it's going to be 1.00 times sine of 48 equals 1.58 times sine of R. And sine negative 1 of R is going to give us sine of 48 divided by 1.58. Take the inverse sine of that. All right. So we want to take sine of 48 sine times 1 divided by 1.58 gives us an angle, a decimal. And now we're going to take the second sine of that, and that's 28.1. So the angle will be 28.1 degrees. So if I wanted to sketch that, I'd go from 1.00 to 1.58. I draw in my normal, and I show this as being 48 degrees, and then this as being 28.1 degrees. So what happens when we do the opposite? We go from a more dense to a less dense. Well, if it slows down going into the more dense, when we exit the more dense into a less dense, it's going to speed up. So if we go from water into air, the angle of incidence is going to be less than the angle of refraction because light is going to speed up. So V increases, which causes R to be greater than I. Now, imagine that you put it in at an angle that it's sped up so much. So if I keep putting it in at bigger angles, right? Angle R gets bigger and bigger. There's a magic angle called the critical angle where it will just travel here, and that this angle here is 90 degrees. It'll just travel along the boundary, which means that R is 90 degrees. And this is called the critical angle because if I put light in at anything bigger than the critical angle, the light will actually bounce back into the material, and that's called total internal reflection. So in this particular case, that critical angle, and this is water, okay, so we're going to go from air to water, 1.00 to 1.33. The way that we're going to do this is we're going backwards. We're not going from air into the water. We're going from water into the air. So this is our theta I, which is called theta C. And this is our theta R, which is 90 degrees. So the critical angle happens when 1.33 times sine of the critical angle is going to be equal to 1.00 times sine of 90. Well, sine of 90 is 1. So sine of theta C is going to be 1 times 1 divided by 1.33. So when we're going into air, it's pretty easy because it's going to be we're just going to take the inverse sine of this. So 1 divided by 1.33. And then we just take the inverse sine of that, which is critical angle is 48.7 degrees. So what that means is that if light enters the water-air interface at something less than 48, we can use Snell's law to figure out what R is. If it enters right at 48.7 degrees, theta R is going to be 90 degrees. And if I is greater than 48.7 degrees, it's going to totally internally reflection occurs. So it's going to totally internally, it's going to bounce back in. So this is the premise of fiber optics. And this is also why when you look at a body of lake, it looks sparkly from the inside, because you do get light that travels, that goes into the water, that doesn't bounce back out into the air, and it bounces off the bottom, and then some of that light is going to try to bounce out at a greater angle than 48.7 degrees, and it will bounce back in. So it can make the water look like it's glowing inside. So basically, if we want to find the critical angle for any substance, we're going to use sine of theta C equals 1 over n of that substance, assuming that it's the critical angle for diamond in the air, okay, in the air. Okay, that assumes that we're going out into 1.00, an n of 1.00. It'll be different. It would be the n that we're going out into divided by the n that we're in, that we want to find the index of. So in this case, the n of diamond is 2.42. So if I want to find the critical angle for diamond, it's going to be 1 over 2.42 inverse sine. And I get 24.4 degrees. So theta C is going to be 24.4 degrees. Now, think about a diamond that's just a nice square, okay? Doesn't have any facets on it. It is very likely that you will get rays of light that will enter this at something bigger than 24.4 degrees, which means that it's going to bend. And if it's at a really big angle, right, it's very likely that the angle of refraction inside is going to be bigger than 24.4 degrees, which means that when it tries to go out, it's going to hit the other side at whatever that angle of refraction is, right? So if it refracts at 24.6 degrees, it's going to hit the other side and try to go out at 24.6 degrees, but that's bigger than the angle of the critical angle, so it will actually bounce in. And it turns out that because it has such a high critical angle, it's really easy to get light to trap in the diamond, which is why diamond has always been such a great gem. If you really want to get the diamond to be super sparkly and you want to maybe hide some inclusions or stuff that's inside of it, if it's not a very good diamond, you can put all sorts of facets on it. And the geometry of that will accentuate and make it more likely that the ray of light will hit at an angle bigger than 24.4 degrees relative to the normal of that side, and it will bounce back in. The other thing I want to talk about is dispersion of light. So one of the phenomena that you may have experienced is if you look through a prism of light actually will separate out white light into its colors. So when you look at white light in the room here, its spectrum is really, it includes all the colors of the rainbow, Roy G. Biv. And if white light passes through something that has sides that are parallel, it turns out that the different frequencies of light, different wavelengths of light, or frequencies of light, have slightly different indexes of refraction. So, for example, red light might have an index of 1.51, but violet light might have an index of 1.53. So just think about the speed of light in these. If I wanted to find the speed of light in red light, it would be 3e to the 8th divided by 1.51. Which would be 3e to the 8th divided by 1.51. 1.99 e to the 8th. And this is the speed of light. The speed of light for violet light would be 3e to the 8th meters per second divided by 1.53. So notice that speed is going to be slightly different. So 3e to the 8th divided by 1.53 is going to be 1.96 e to the 8th meters per second. So there's a slight difference, which means that even though these sides are parallel, there is a little bit of difference going on in how much they slow down, which means they don't bend at the exact same angles. They bend at very, very slightly different angles. They slow down a little bit more. Violet light, higher frequencies slow down more. And when we say that the index of refraction for glass is 1.51, that's an average value for all those colors of light. But if we were to change the geometry a little bit, and now we put white light in, when these bend, you can kind of accentuate the difference between the bending, and you'll see that red pops out first and then violet's the last. Well, actually, violet pops out first and red is the last. Violet bends more than red light, and you can actually see that effect when you look through a prism. You can separate light out into its colors. And this is what's happening in a water droplet. In a water droplet that creates a rainbow, you basically have a water droplet. And if you think about the sides of the water droplet, they are kind of like a prism. So if light hits them just at the right angle, white light from the sky, then you will actually see that pop out as like that, and you'll see that rainbow. And so that's what's causing the rainbow, is the dispersion of light through water droplets. And especially since water droplets tend to not be, as they fall, they get distorted. They're not just round. So there's even more of that effect.